Hello everyone, my name is Austin Rovinsky and I'm an assistant professor at New York University. This is the 14th lecture in my mini course on physical design databases, and this lecture will focus on providing an overview of the current OpenROAD tools available. So here I have OpenROAD's GitHub website opened up, and I'm essentially just going to walk you through the README and show you what's here. So if we scroll down to the README content, one of the first things that we see is a simple flow diagram showing the order of the tools that typically get run. So we can see up here that we have, the Verilog, your libraries, constraints, all of your input files, your libs, lefts that we've discussed in previous lectures, and then that goes into the main part of the flow. So the first step here is synthesis, which is actually not part of the OpenROAD tool. This is part of the YOSAS tool, but it is used in OpenROAD flow scripts. And then the rest of the tools here are part of OpenROAD that we have. So we have the floor planning step, the placement step, clock tree synthesis, routing, and finishing. And then there is a final GDS2 file. This is your chip layout file that will typically come out at the end of the flow. This is the layout file that you give directly to your chip manufacturer in order for them to fabricate it. So I'll be discussing each of these steps in a little bit more detail and showing you where the source code lies and details like that. So if we go down a little bit, I like this flow diagram a little bit better. It shows specifically OpenROAD flow scripts and the steps that are implemented there in more detail. So we can go through each step here. And first we see that there's, aside from synthesis, which is not going to be covered in much detail, it's outside of OpenROAD because it's using the YOSAS toolchain. We're going to look instead at floor planning. And essentially what floor planning is doing here is it's really initializing your design. You're basically doing this initialization step where the user will specify what are the area constraints on your chip, how are you setting up your cell sites, your cell rows, any margins, basically setting the stage for where everything can be placed, where are going to the pins for the design going to be placed. So you have your list of inputs and outputs. Those should come from your RTL, your Verilog code, etc. And then you'll decide where those get placed. And then you'll actually first make decisions about any large macros in your design, where those will get placed. So macros are things that typically do not fit in standard cell rows, the DB rows that we have, and so they'll get placed first because we need to lock in their positions. We'll do something called tap cell and well tie insertion. Those are special cells that are required for manufacturability. So these aren't part of your RTL logic. These are what we call physical only cells, meaning that they only are used in the physical implementation part of the chip. And there's a few different instances of that, of these physical only cells being used, but this is one of them. And then we have our power grid generation, our power delivery network or PDN generation, and this will try to create a nice grid so that so we'll have metal connections so that it can effectively deliver power to all of the different instances in the design. Because unlike in the logical land where we care mostly about the connections between cells or instances, we also care about making sure that all of those have power delivered to them here. So the next step that we'll have is placement. And first we have global placement and then detailed placement later on. So global placement is essentially just trying to take all of your instances and then place them onto this grid that we've created for the chip. So we talked about DB rows, DB cell sites, and all of those form essentially the locations which instances can be placed. So now there's an algorithm which goes through and it tries to roughly place all of them in that area. And it doesn't do a very good job of making sure that they don't overlap. It just kind of makes sure that they get in the generally right area. And then we have detailed placement later on, which will do something called legalization, and that actually makes sure that all of those cells are snapped to the cell sites so that they're legal, they're in a good location, they're not overlapping with each other, etc. And then in between those, we have some resizing and buffering. So this is a timing optimization algorithm, which will try to make sure that that the timing looks good. So if you've discussed setup time, hold time, maximum frequency in some of your digital design courses or previous experience, this is what this is trying to help with. Then the next step that we have in here is clock tree synthesis. So unlike in digital logic only land or purely logical area, we have to make sure that our clock, which is timing all of these circuits, arrives at roughly the same amount of time at all of the registers or all of the other sequential elements in our design at the same time. And so because we're working with wires, which also have this intrinsic delay to them, we need to make sure that we're sort of constructing this tree structure to try to make sure that all of the endpoints of this tree are hopefully balanced, so that when you send a signal from the top of the tree down to any one of the leaves, any one of the leaf nodes, that they all can roughly arrive at the same time. Then we have some more timing optimization here, some filler cell insertion, and that filler cell insertion, that's another physical only cell, so that's just to, again, make things good for manufacturing purposes. And then we move on to routing. Now that all of the cells have been placed, we've done some routing on the clock, or we've inserted the clock tree. We do some global routing followed by some detailed routing. So here, we're generally just trying to make sure wires are in roughly the right place for the global routing, which is to say there's not too many wires in any one area. We call that over-congestion. If an area has too many wires, it's over-congested. So this first step is just trying to take a first pass at the problem, make sure the wires that are routed from any instance to any other instance not too over-congested. And then detailed routing fixes all of the routes to their actual locations. So this is mainly trying to avoid design rule violations. So in the dbtech file, when you load your left file, there's a whole bunch of rules on how you're allowed to route wires. And detailed routing will try to follow all of those rules while still connecting all of your instances together. And then in the finishing stage, we have a few different steps here. These are mostly for manufacturability purposes. Metal fill insertion, doing a sign-off timing report, trying to make sure that your reports are accurate, that the way you've done timing analysis is accurate, and then ultimately generating that GDS2 file, that chip layout file. So that's a majority of the flow and how everything works and how all the tools are orchestrated together. And there were some allusions to this when we first discussed OpenROAD. But I want to talk about each of these steps. So importantly, the reason why each of these steps were mentioned is because each one is done by one or perhaps even a couple of different tools. So we discussed floor planning. Floor planning is done by a specific tool. Global placement, detailed placement, all of these are specific tools that execute on the OpenROAD database, the OpenDB, in order to accomplish all of these tasks. And so there's a good likelihood that if you create a new ADA tool or you want to work on top of an existing tool, that you will probably use one of these tools, you'll develop with one of these tools, or at least use it as a reference. So each of the tools that you see here are all listed. And just for a quick demonstration, you can of course read this on your own, but you can see what the chip layout looks like in these screenshots of the OpenROAD GUI after each step. So after floor planning, you can see that we have our full chip square here. And on top of that, you can see on the yellow triangles and green triangles coming from it that these are the input and output pins that are all coming from the design. And then all this the sort of cross hatched, the left and right colors that are going down here, those are part of the power grid. So each of those are specific metal layers. Each one's represented with a different color. So you can see here, like there's a MET1, which is short for metal layer number 1. That's in red. We also have a via between metal 1 and metal 2. That's the same color. And then we have metal layer 2. That's in green. And then so on and so forth. And so different technologies will have different numbers of layers, but you'll be able to see them here in the GUI. Then if there is macros, or if there are macros in your design, you'll see some automatic macro placement results here. And so it will try to take all of those macros that are in the design and then place them in a way that makes sense. And we also have congestion heat maps. So these are tools that will color code the areas to see how dense things are. In this case, it's placement, so how many cells are in the same area, but you can also see here that you can also do the same for power, for routing congestion, something called IR drop, which we won't discuss in any detail here, but those are all available. For clock tree synthesis, you can see that there's a clock tree that's constructed. So on the right here, there's a logical view where you can see all of these red dots are sort of the endpoints, and it's trying to balance between them. So there's some that are balanced here, and then some that are balanced at the bottom. And then over on the left here, we can see a physical representation of that. So this is you can see the fan out, the electrical fan out from one cell or one clock buffer, which is then fanning out all of the wires all over the place. And different colors here represent different layers. So red is probably the wires coming from the first layer of the clock tree, versus yellow might be second, or green might be third. So you can see sort of how the clock tree fans out. And then in routing, we now have all of the detailed routing. So if you look closely here, you can see that there's some more green, some sort of maroon type colors, some of the cyan, which shows all of these signal wires have now been routed. They have physical shapes associated with them, and it does kind of look like this blob just because there's so many wires connected to so many different instances on this design. And you can see right here as an example, in this browser window, we can see that there are about 15,000 instances in this design. So there's at least 15,000 wires connecting all of those together. And so that's the main part of the flow that you'll see here in the README, and you can try on your own. And then one last thing that I want to do is to just go into the source folder to show where all of this code actually resides for all of these tools. So you can see here that there's a lot of three-letter codes in here. Each one of them is the sort of code name that's associated with a tool. So every tool in OpenROAD will have a three-letter code that's associated with it. Hopefully it should be sort of a shortening of the full name of it. So for example, ANT, A-N-T right here, is short for an antenna checker. So that's something we didn't really discuss too much, but perhaps one that we have talked about. DRT is short for detailed router. So this is the tool that's responsible for creating the exact set of wires and shapes that connect all of the instances together. We've also talked about GRT, global router. IFP, that's floor plan initialization or initialize floor plan. And you can see that there are several other tools which are either have a more niche purpose or they we haven't just gotten a chance to discuss them yet. And so perhaps if we take a look inside one of these folders just to see how it's structured, this should be a fairly similar structure to how we created our own tool. But just for example, if we look inside the detailed router, we can see that each one is going to have its own README file, which discusses sort of what the tool does, just like how we discussed a moment ago. And it should cover what are the commands that are hosted by this. So this is a command that's in Tcl. So if you're a user and you have the shell interface open, the Tcl shell interface open, then you can run this command and you can use these optional flags all throughout here. And you can run that individual command. So here we see that the detailed route command is the one that's supported here. Lots of different arguments in here. And then there should be a description of all of the flags, the argument switches, and a short description at least of what they do. And additionally, sometimes if you're a developer and you want to have some very fine-grained insight into how the tools are working, sometimes there are debugging options. So for example, for the detailed router, you can set an optional debug flag with one of the sub-steps that we haven't discussed to look at more details about how each of the detailed routing sub-steps is working. So there's a whole bunch of arguments that you can provide here. And in general, all of these tools should come with either some example scripts or some regression tests. And so those will be located in a common test folder. We have the source folder, which has all the code for the tool. And then we have an include file, which in case any other tools need to use the code or the functions that are in here, this is where they can be exposed. And sometimes there should be docs, some documents, and some either how-to guides or readmes or other useful documentation to make the tool, to help use the tool. And so that about wraps things up from here. So thank you very much. This should be the last lecture in the series. Thank you very much for watching everything. Hopefully you've been able to learn some useful skills and you feel that you can start contributing either to your own EDA project or OpenROAD as a more broad project. So thank you very much for watching. I'd like to thank NordTech, whose funding made this video series possible, and I'd like to thank you for taking the time to watch it. Take care. Bye.